Hello, how is everybody doing? Hey, very nice.
As ever.
Albert E. Holy moly, that's a lot of people.
Hi, Rishi.
Hello, Samuel. Why don't you turn on your camera? We want to see you guys. Hey, we got Samuel, we got Noe. If you guys are willing, turn on your cameras. Hey, we got Albert E. Very nice. Okay. So, we will get started shortly. Let me figure out my setup first. Okay. Okay, very nice. How's everybody doing today? School good? Okay, nice. Dude, Mr. Abe held me in for like 5 minutes after class. It's so bad. Okay, I will screen share and then Jeffrey, you could, actually I will do the introduction. So, could you all see my screen? Yes, no, maybe so?
Yes.
Okay. So basically today we are going to be presenting on algorithms, and this is probably the main focus of the club for the first semester because algorithms are really, really cool. So basically we'll talk a bit more about it, but before we get into that, we finally have the competition website up. So essentially we're doing something new this year, and basically what we're going to be doing is to incentivize you guys to participate. There's going to be challenges and you guys are going to have to solve them, and then you can submit for points over here. So let me just do a quick demo of the website. So you just go to cdf.shscsclub.com and you'll be taken here and you have your challenges, for example. So what you could do, and the first meeting is like the flag is already in the Facebook group. So I'm just going to show you guys how to submit. Let me see. So basically all you got to do is you copy and paste the flag in here and it'll show you that you got it right. So we'll have a bunch of challenges. You can see there's a lot of them here. So just log in, make an account, and you guys could submit your flags. Okay. Jeffrey, you could take it from here if you want.
Yeah, sure. So first of all, right, an algorithm is obviously it's like a series of steps that you might take to like complete a task, right? So you might wonder like, why do you go so in depth into these algorithms? Well, mainly it's just to do things like more efficiently, right? So like here you can see if you can optimize algorithms, you can solve problems super fast, and you don't need to have like gigabytes of storage necessarily to like solve a problem. So basically, yeah, it just makes life better.
Hold up. No. Let me go back.
Yeah. I think the classic example to like why algorithms is important, say like Google, right? Google searching. If Google went through like every single one of their billions of entries, it would probably take a lot longer than a second to like fetch results, right? So yeah, this is why we study algorithms and why they're super cool and super important.
Yeah, so basically, like as Jeffrey said, there's two ways to speed up a computer, right? You can either make the hardware better, right? Or you can make the software use the hardware better. And like right now, according to Moore's law, we're supposed to keep getting faster transistors, but our transistors are already like atoms wide, right? So essentially that's not going to last very long. So essentially the best way to get these speed ups is to improve the code you're running. And as you'll see, there's a lot of really clever ways that people have been using code to speed things up. So let's just do a live demo. So this is going to show you guys exactly having algorithms useful. So as a refresher, the Fibonacci sequence is basically the first term is 0, the second term is 1, and the following terms are all summed, right? So 0, 1, 0 plus 1 is 1, 1 plus 1 is 2, 2 plus 3 is 5, and so on and so forth. So let us first try to code this up. Let me go to a REPL real quick. So we are going to do this in C++. Okay. So does anybody know what it's called when you define a series in terms of its previous terms?
Recursion.
Anybody?
Recursion.
Yes, it's called recursion. And what does that mean in coding terms? That's a math term, right? So what does it mean to do recursion in coding?
Recursion. I mean,
So,
like,
well,
don't
I
you
mean, try to explain it. What's a good way to explain what recursion means?
It's
In
like
code.
calling your own function in the
Uh-huh.
function, sort of.
Yeah, exactly. So essentially what we're going to do the first time is just call Fibonacci of previous functions, right? So if we call Fibonacci of n, we want to find the sum of Fibonacci of n minus 1 plus Fibonacci of n minus 2. So the most obvious way to do that, right, is just to write a recursive algorithm that calls itself. So over here, we're going to have an int Fibonacci, and it takes in an integer n, right? And essentially, we have to have, what do we need to write a recursive algorithm, basically?
Base case
Yes. And why do we need a base case?
to prevent stack overflow.
and
Yeah,
they'll
because
just go on infinitely.
exactly, if we always tell it to find Fibonacci n minus 1, right? But there, it never like returns an actual answer. It'll just go like Fibonacci negative infinity, and we'll never have a stopping point. So we do need a base case. So if n is equal to 0, then we return 0. And if n is equal to 1, we return 1. Okay. And then all we got to do is write a recursive algorithm, Fibonacci n minus 1 plus Fibonacci n minus 2. Okay, this seems like it would work, right? What's the problem here? Did I spell it wrong somewhere? Oh, I did spell it wrong. Okay, we're good. Okay, so essentially now, if we run our thing, we put like 4. That makes sense, right? 0, 1, 1, 2, 3, it's working. Let's try like 10 maybe. Okay, still working pretty fast. What happens if you do like 40 or something? Okay, well, this is clearly not going to work. It took like 2 seconds. If we even go a little bit higher, maybe like 60 or something, you can see it's going extremely slow, and this is not going to work. And why do you guys think that is? Why is it so slow? What's the problem?
Repeating operations.
Exactly, we're repeating operations. The whole point of algorithms is that you want to do as little operations as possible because a computer takes time to do operations. A computer can't do infinite number of operations every second. So essentially, let me just print out what n is each time. And let us do it for Fibonacci 10. We'll probably should put an end though, okay. Okay, so you can see it does 9, 8, 7, 6, 5, 4, 3, 2, 1, not bad. 0, 1. What we're doing? 1 again, 2 again, 1 again, 0 again, 3 again. So you can see it repeats over and over and over again, and clearly this is a waste of space and time. So what do you guys think we could do to not have to redo it every single time?
DP.
That is one way. So essentially what he says to do is to store the actual value somewhere. So what we're going to do is we're going to make an array. So we'll do int. We'll call Fibonacci's 100, let's say, and we will basically say, okay, so we'll say Fibonacci 0 is equal to 0, and Fibonacci, and Fibonacci 1 is equal to 1, and we'll do a for loop for int I equals 2, I is less than n, less than or equal to n, I plus plus, Fibonacci I is equal to Fibonacci's I minus 1 plus Fibonacci's I minus 2. Okay, and all we got to do is return Fibonacci, oh my god, Fibonacci's n. Okay, now let's run it. Let's see what happens. Hopefully, it's down here. Okay, okay, so we're going to try 60. Did it in like snap of a finger, right? didn't take any time whatsoever. You can see that just by changing the way we approach a problem, we were able to speed it up by so much. We could even go way higher. We could go like 120. I mean, you might have integer overflow, but yeah, there is integer overflow, but it does it really, really fast. So essentially the point is just by being a little bit smart about it, we could save a ton of time with algorithms.
Wait, how come your REPL works so fast? Like when I do it, like I always have to wait so long. And then like when I press it, I have to wait like seconds before it actually like displays the thing.
I think for longer, I mean, it has to compile first. I mean, it's never been that bad for me. I don't know. Maybe we could look at your REPL later outside of a meeting. I don't know. Okay, so that's basically all I wanted to show for this demo. Actually, do we want to do something else? Well, okay, so what happens if we only wanted to run one Fibonacci thing and we didn't care about any of the previous Fibonacci numbers? Right now we're storing all the previous numbers, but we don't really care about them. So how could we not store all of them? Ideas?
Just remember the top two.
Exactly. All you need is the last two numbers. So why in the world should we have to store all the previous numbers if we only care about the last two numbers? So I'm just going to do that real quick. So we're just going to do int n2 equals 0, n minus 2 is 0, and n minus 1 is equal to 1. And then for 2 is less than or equal to n, we'll do int temp is equal to n1 plus n2. And and then we're going to shift everything over. So n2 equals n1 and n1 equals temp. And then at the very end, all we got to do is return n1. And now if we try 120 again, we get the same answer, and we didn't have to even use this array. So basically, we're saving a lot of space. So there's two things you got to consider for algorithms. You got to consider your space, and you got to consider your time. Okay, I think now we could go back to the presentation. Oh, I stopped sharing my screen? Oops. Okay. All right, so now in the chat, could you guys put like how would you find the max of an array? Give me like as many ways as you could think of. You know, I can't look at the chat. Jeffrey, could you read me what they're saying in the chat? Because I cannot read the chat from here. Or can I? Oh, no, actually I could. Okay, pretty good. Linear scan using the built-in max function. Dude, Oliver, there's no built-in max function for C++. You had to use, in Python there is, but unfortunately we're not using Python. Okay, that's one way to do it. What's another way we could do it other than just a linear scan? Binary, what does binary mean? Okay, sorting is what I was looking for. So basically the two ways that I thought of when you're doing a max is you could either sort the array or you could just go through it and keep track of the biggest number you've seen so far. Now, could someone tell me which one is better and why? Say it out loud.
Linear scan, because sorting is n log n.
Okay, so like, okay, tell me like why logically it's worse, right? Because yeah, I get that it's n log n, but what work is it doing that we don't need it to do? What extra work is it doing? Does anybody know? What extra work is sorting doing that we don't really
need to sort the remaining elements, right? Once you have
exactly. The only thing we care about is the biggest element, right? Why do we have to like order the rest of the elements? That's a waste of time. So whenever you're thinking about solving these algorithm problems, you have to see what's the minimum amount of work we're doing. If all we want to find is a max, there's no reason to sort the rest of the array. It doesn't make any sense whatsoever. So essentially, when you're doing this, the best thing to do is always to just do the minimum possible. And in this case, is look at each element once and see if it's the biggest one we've seen so far. Go ahead, Jeff.
All right, so we might want like a quantifiable way to like see how an algorithm runs, right? Like it's kind of helpful if you say it runs slow or it runs fast, but it'd be nice to like determine what is slow and what is fast, right? So this is where big O notation comes in, and it basically what big O notation basically is like basically how well does a program do, especially when you feed in large inputs, right? So for example, O of n, that would be like a linear scan because you're looking through n elements, right? So you do n operations. So that's an O of n runtime. Binary search is O of log n because what you'll do is you'll like keep having, and so basically the number of operations you need to do is proportional to like log base 2 of n. And like also of n squared, like it says here, if you loop through pairs of elements, then you have n choices for the first element and n choices for the second. And I guess like if you don't care about the order, you can divide by 2 or whatever. But yeah, this is looping through pairs is O of n squared. I guess like another example, the Fibonacci or the inefficient Fibonacci solution is exponential time. It's technically like phi to the n, but yeah, it's exponential time with our inefficient solution. So that's very bad. But with our more efficient solution, that just use like an array, right? Or I guess memory optimization. That was just O of n because you're just calculating f0, f1 all the way until fn. So yeah, that is how our algorithms differ.
Yeah, so the reason why Fibonacci is exponential is because essentially you're just splitting it every single time, right? Like you're doing n-1 and n-2, you're splitting it in two, and you're splitting it in two each time, and that's why it's exponential and that's why it's bad. Also, we're not going to talk about this necessarily, but there's also big theta and big omega, and these things are not that important when you're talking about USCO, but essentially the difference is that big O notation is worst case, okay? So like worst case means that if everything possibly goes wrong, how long will it take? Now, the thing about USCO algorithms is that none of them have any randomization whatsoever, and essentially it's always the same. But if you have a randomized algorithm like Quicksort, for example, it might run in O of log and O of n log n time normally, but in worst case scenario, it'd be O of n squared. So essentially, your big omega is the best case, and then big theta is just like the range between big omega and big O, basically, but it's not that important. Yeah, Jeff, you could do this one.
Yeah. So you might want to like, or you might wonder, right? Like, how does big O apply to those epic contests like USICO, right? And so generally USICO gives what is it, I think like 1 second for C++, and for 1 second to C++, you can usually do around 10 to the 8th. That's 100 million operations. And so this means that like if you look at the bounds of a USICO problem, you can, if it's like silver or above, you can probably tell what like general runtime they might expect. So for example, if they say, or if they give you a variable n, and n is like very small, right? Like less than or equal to 11, then you can probably expect to submit a solution that will pass with O of n factorial runtime, because n is very small, right? But if n was like a lot larger, like say 10 to the 5th, then you would probably need to write an O of n log n solution. So this might include like sorting or maybe use some ordered set or like something like that, right? So I've listed some bounds here, but usually the most important ones are the ones in bold there. So O of n squared, O of n log n, O of n. You'll probably want to remember these bounds if you're doing USICO.
Okay, so just some practice. Can anybody tell me what the O of n runtime of this algorithm is? Anybody?
N.
Yep, and this one? Anybody? Go on, say it. Don't be shy.
Squared.
Yeah, n squared. Did everybody see why it's n squared though? Because basically you have a nested for loop. So you gotta run the inner for loop n times, and it's run, the inner for loop itself is run n times. So you gotta run something n times within another n times, so it's n times n, which is n squared. What about this one? That's a bit more tricky. Anybody?
Log n?
Yeah, what base log n?
10? Yeah,
Well,
10.
yeah, so it's log 10 of n. Because every time we go through this while loop, we're dividing n by 10, right? So essentially, if it's basically log to base 10 of n is basically how many times we could divide n by 10. So that's why this is log n. Does anybody recognize what algorithm this is, what it's doing?
Summing the digits.
Yeah, so basically what it does, it takes the last digit, which is n mod 10, right? Because like we're working in base 10, right? So if you take n mod 10, you get the last digit, and then you add it to your sum, and then you cut off the last digit by dividing by 10. Okay, what about this one? Basically the same thing. Anybody?
Oh, it's like converting to base 3.
Kind of. Well, basically it's just us like finding what power of 3 something is, but yeah, that's basically all it is. So that's log 3 of n. And then does anybody remember what we said the what do you call the O of n, the runtime of Fibonacci, the bad way is?
2 to the n?
Yeah, it's essentially 2 to the n. It's technically 5 to the n, which is like golden ratio, but it's not. Yeah, it's basically exponential. That's the main thing. And then this one, what's the better implementation? What's the complexity of that? Anybody, come on, new people.
And
Yeah, it's n. Unfortunate. Okay, so now let me just show you how it actually works. So let's look at it in real life. So if I go back to my REPL, let's see, where's my thing? Okay. So essentially what I've done is I've set up a clock. So essentially it'll take the time here, it'll take the time here, it'll subtract it and tell me how many seconds it took to run. So why don't we try an n algorithm. So for int I equals 0, I less than n, I plus plus, and all we're going to do is just do x is equal to 2 or something. Int x is equal to 2. So essentially, if we just run this and let's put like 10 to the 9, okay, 1, 0, 0, 0, 0, 0, 0, 0, 0. Okay, let's see. Maybe that's too big. Let's do 10 to the 8 actually. How about that? Okay, so well, this is 10 to the 6, and it took 0.002146 seconds. So how much do you think it'll take if I do 2 times 10 to the 6? Anybody?
2 times the amount.
Yeah, because essentially it's in n, it's linear in n. So if we double the amount of operations we do, we're doubling the amount of time it'll do. So if we do that, you get, it went from 0.2002 to 0.004. But what happens if we made this an n squared algorithm? Let's do for int j equals 0, j less than n, j plus plus. Okay. So now if we do 10 to the 4, let's do, it's 0.2249. What do you think it's going to be if we double the input? Someone new, please. I beg. Anybody? Come on. If you're doubling it and it's n squared.
4 times.
Yeah. Come on, you guys gotta participate. Come on. Okay. So essentially we do 2000. You get 0.008. So you can see that it's worked. That's exactly what's happening. So that's just a cool demonstration to show you guys how, like, basically the problem is if something increases that much faster, it's a much worse algorithm, right? Because if we just increase how much we want to like accomplish with it by a little bit, we're already spending way more time, which could get problematic if we ever get bigger data, and bigger data is what we're getting right now. So essentially that's why algorithms are pretty important. Oh, I stopped sharing screen again. Okay, hold up. Okay, so now we're gonna talk about a USAGO example because this will show a little bit more about how you could actually apply this to coding competition. So let me show you the problem actually. You guys see my screen? Okay, so let me just break down the problem. Essentially, it's saying that it's basically saying that a cow is competing in a cross-country skiing event, and basically she starts out with a certain speed, but she begins to slow down over time, and she has events when she slows down. So she can either slow down at a certain time or a certain distance from the starting point. So the main problem with this is that you can't figure out which events happen first because there's 2 different measurements for it, right? There's either time or by distance. So could anybody tell me what would be how how do you find out which one is first between a distance or a time thing? Like, what would be your approach to doing this? If okay, let's just say we only had time events. How would you sort the time events? You basically just sort it normally, right? So you could sort the time events normally. You could sort the distance events normally, and essentially what you could do is you could just go through all the possible pairs, right? You check, is this time event before this distance event? Is this time event before this other distance event? Until you find the one that works. But this will take how long? Does anybody know if we're comparing every single pair of events? Anybody? Pair events? Well,
Square.
yeah, it's basically n squared. So since you have n squared time, this is going to be way too slow because like, well, it's fast enough for bronze, but it's not the best way to do it. So essentially what you would want to do instead is to sort each one individually. Now you have your times all in order. You have all your distance in order. And you know that the next thing that happens has to be either the first time or the first distance. So essentially the idea is that if you only if you sort things and then compare them, you could actually find a much faster way of doing it. Jeffrey, is there anything that you want to say specifically? Wait, let me go to your slide. That's basically it, right, Jeffrey?
Yeah, I think so. Wait, this was CD slide, but yeah.
Oh, sorry, Duty.
Yeah, that's pretty much it.
Okay, so essentially we have a really quick challenge for you guys. Whoever answered it first will get the winner flag. And essentially this is just a really quick coding test. So what you want to do is you want to find the digits of the binary representation of this. And private message me your answer, and I will give you the winner flag if you're the first person to get it. Also, private message me if you guys need help because we kind of went through that fast. So just let me know. Oh yeah, you can use any language you guys want.
Wait, we're supposed to code this?
I mean, unless you want to manually convert it to binary and then figure out the sum. So, I mean, if you
Okay,
want.
never mind.
Okay, I'm getting some answers. Let me just check if they're actually correct. Because I am getting a different answer from you guys. Hold up. Okay, well, wait, let me let me just manually do this. Okay. Wait, are you guys using the right number? Because I'm getting a very different answer than you guys.
Wait, I'm using the number on here.
Well, they should be the same number. Yeah, they are the same number. Okay, wait, hold up. Okay, could officers send me what they got? Like, could you guys do it real quick and send me what you got? Because I'm getting a different answer. Okay, well, we have a winner, Brian Lee. Congratulations on being the first to answer 20, which apparently is correct. Okay, very nice. So I will send you the winner flag. Everybody else is free to go, but just as a reminder, we have a bunch of challenges on the website, and those are basically your assignments for next week. I'll post a recording of this, and I will also post a link to the slides, and I will also post other assignments that you guys could do if you guys want. So other than that, you guys are free to go. Thank you guys for coming. Hope it was helpful. See you guys. I'll send Brian the flag, so give me a sec.
Dang, you should have continued sharing your screen.
No, I'm not giving you all the flags.
I did not code it.
What?
Wait, how are we supposed to get like the participation flag?
Wait,
I will post it in the Facebook group. I forgot about that, but
how do you get the flags from solving the questions?
for which ones?
Like
The
if you
Fibonacci one?
solve Fibonacci 3, like what do you do?
First go to Fibonacci 1. It explains what you're supposed to do.
Oh, okay.
Let me send Brian this flag first. I will post the other flag in there. Okay, there's your flag, Brian. I hope you enjoy. Okay, yeah. See you guys.